Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about the central limit theorem, which is a fundamental result in probability that states that sums of independent quantities are approximately Gaussian. We're going to provide some intuition about why the central limit theorem holds, and we're going to show some examples illustrating the application of the Gaussian approximation provided by the central limit theorem to probabilistic modeling and to statistics. Let's get to it. We're going to talk about the central limit theorem, but to begin, I want to remind you about the law of large numbers. What does the law of large numbers say? It says that if we have a sequence of independent random variables which have the same mean mu and finite variance, then if we consider the sample means of the first n entries of the sequence, which we denote by mn, then that random variable is going to have a mean that is equal to mu, and more importantly, it's going to have, or equally importantly, it's going to have a variance that decreases linearly with n, which means that its distribution is becoming more and more squashed around mu. By Chebyshev's inequality, that implies that the probability that the sample mean deviates from mu by a certain constant, no matter how small the constant is, so this holds for any constant greater than 0, no matter how small the constant, that probability is eventually going to go to 0 as we increase n. And that's the law of large numbers. If we look at the implications of the law of large numbers when we're estimating a population mean from random samples, we can visualize it like this. When we take random samples and we compute the sample mean of the random samples, we fall within the law of large numbers because the random samples have mean equal to the population mean and variance equal to the population variance. As we average over more and more samples, what we observe is that the sample means, here we see each of these dots is a sample mean computed from the height data that I often use to illustrate these things. We see that the sample means as n grows eventually are confined to be epsilon close to the population mean as predicted by the law of large numbers. However, the law of large numbers doesn't tell us what the behavior of these sample means is for a fixed n. We don't know what the distribution of this sample means is here. And that's what we need the central limit theorem for. To drive this point home, we can take a look at this Chebyshev bound that we use to establish the law of large numbers. The Chebyshev bound says that the probability that there's a certain deviation of epsilon between the sample mean and the population mean is bounded by the population variance divided by n and divided by epsilon squared. We can actually go to our height data, for example, and evaluate these quantities. This one is easy to evaluate. We just fix epsilon to be, let's say, half a centimeter. And then we can do this for several n's. We can just evaluate that quantity. We know the population variance because in this case, I have this ground truth data set that we used to play around with. For this quantity on the left, what I can do is I can take n random samples and do this over and over. So that I have many batches of n random samples. And then I see how often this event holds. We see a deviation between the sample mean and the population mean of more than epsilon for that fixed epsilon. This is essentially the Monte Carlo method applied to approximate this probability. And if we do that, we can check how good this approximation is, which is why are we doing this? Because this is the approximation underlying the law of large numbers. So essentially what we're saying is, how is the law of large numbers at actually approximating a probability related to the sample mean? And it's actually really bad. This Chebyshev bound underlying the law of large numbers is indeed a bound, right? So here I'm showing you the actual probabilities that we estimate with Monte Carlo. And this is the corresponding bound. So obviously we have proof that this is the case. So thank God. The bound is above the actual probability, but it's not a good approximation. And it goes to 0, right? We also have proved this. So this shows you that the law of large numbers does not provide good probability estimates about characterizing the behavior of the sample mean for fixed n. And because of that, we need the central limit theorem. In particular, what does the central limit theorem do? It tells us about the distribution of the sample mean. How does this object behave for fixed n? In order to understand how this object behaves, we're going to have to look at sums and in particular averages of random variables. We did all the work in a previous video where we kind of worked through the distribution of the sums of independent discrete random variables and continuous random variables. Now I'm going to remind you about those results pretty quickly. So if you want to know more about them, just take a look at that video. Okay, so if we sum two discrete random variables that have integer values, the PMF of the sum is going to be equal to this quantity, which is the convolution of the individual PMFs, which I'm going to do this with my hands. Again, you can go look at that video for more details, but essentially what we do is we fix one of the PMFs and we run the other one over it, which has an effect of kind of smoothing that PMF to already give you a little bit of intuition. When we sum n discrete random variables, we're convolving all of their PMFs together. Let's take a look at what happens numerically for an example. We're going to take this PMF, which represents the number of points gained by a soccer team in a game, but that's not too important. And we're going to convolve it with itself in order to obtain the PMF of a random variable that is basically a sum of n of these random variables. So for 2, this is what it looks like, 3, 4, 5, 6, and very quickly, 7, 8, we see something very Gaussian-like emerge. In order to confirm that this is in fact Gaussian-like, we can derive the mean and the variance of the nth random variable that is equal to the sum of these n individual random variables, and we can overlay a Gaussian with that mean and variance on top of it. And what do we see? Obviously at the beginning the approximation is not great, but pretty quickly the approximation is actually really good, even for just 8-9 games. What happens for continuous random variables? The sum of two independent continuous random variables, the PDF of the sum is equal to the convolution of the individual PDFs. Okay, as you can hear, my daughter has woken up. So unless she makes a lot of noise, I'm going to actually continue. You'll have to forgive me for that, but I've been trying to record this video all day and my building has been completely crazy. So let's try to continue. Okay, so what I was saying, the PDF of the sum of two continuous random variables is the convolution of the individual PDFs, which is again, kind of intuitively, we fix one of the PDFs like we were doing for the discrete random variables, and we run the other PDF over and integrate. In the case of the discrete random variables, we're fixing a PMF, running the other PMF over and summing. This kind of smooths the PDF, which is why we're going to see it produces this Gaussian-like effect. When we have a sum of n independent random variables, the PDF of the sum is the convolution of all the individual PDFs. Let's take a look again at what happens numerically. Oh, actually, I jumped the gun there because we're actually going to look at and this is important because we're interested in sample means. We're not going to look at the sum in the case of the continuous random variables. We're going to look at the sample mean obtained by dividing the sum by n. When we divide by the sum by n, the effect is just scaling the PDF. Okay, so this is the PDF of the sum. The PDF of the average or of the sample mean is just equal to n times the PDF of the sum, and then there's this scaling within the argument that scales it back because we have divided by n. Basically, that's what it's doing to the PDF. So the take home here is that we still have a convolution between the individual PDFs. Let's take a look at what this actually looks like for an example where each of the individual PDFs is uniform between 0 and 1. The example is about some coffee suppliers, but anyways, we're basically summing random variables with that are uniform in the interval 0, 1 with each other. This is the first one. If we sum 2 and dividing by n, what we see is this, and then this, and then this, and then this, and then this. Again, for already the sum of 6 uniform random variables between 0 and 1, it looks very Gaussian. Again, let's take a look at what a Gaussian approximation overlaid on this would look like. I think I said sum, I meant the mean. Okay, this is an average. This, just to be clear, this is an average of 6 uniform random variables. let's take a look at the mean of the average. It's just equal to the mean of each random variable, which is 0.5, and the variance is the variance of each random variable divided by n. Okay, the variance of a random variable that is uniform between 0 and 1 is 1 over 12. Now let's overlay this Gaussian that has the same mean and variance, and what we see is that the approximation becomes very good very fast. Already for 6, it's actually very, very good. So what does the central limit theorem say? The central limit theorem says that what we observe numerically is guaranteed to hold theoretically, in the sense that if we have a sequence of independent random variables that have the same mean mu and variance sigma squared, and we look at their sample mean, as we did for the law of large numbers, we already saw that that sample mean has mean mu and variance sigma squared over n. Okay, and this over n is what guarantees the law of large numbers, what gives us the law of large numbers. But now what we say is, what is the distribution when we stop at a certain n? And the central limit theorem says that eventually that distribution is going to be Gaussian with mean mu and variance sigma squared over n. Unfortunately, proving the central limit, did I say the law of large numbers? I hope I didn't, but let me repeat that just in case. The central limit theorem states that the sample mean converges in distribution, or has a distribution that is approximately Gaussian with mean mu and variance sigma squared over n as n grows to infinity. We're not going to unfortunately prove the central limit theorem because the math gets too complicated for me to explain in this video, but at least I want to explain to you what would be the actual mathematical statement that we would prove. For that, we have to remind ourselves that when we scale a Gaussian by a certain constant alpha and we add another constant beta, what happens to the Gaussian is that its mean is multiplied by alpha and we sum the additive constant, and the variance is multiplied by alpha squared. So my statement that the sample mean tends to have a distribution with mean mu and variance sigma squared over n is equivalent to saying that the standardized sample mean, where we subtract this mean and divide by the variance, has a Gaussian distribution that has mean 0 and variance 1. Remember that when we standardize, we obtain a random variable that has 0 mean and standard deviation or variance equal to 1. So now we can actually get a better idea of the statement that is proved in the central limit theorem. We can take a look at the CDF, the cumulative distribution function of this guy, and what we would show is that if we look at a sequence of these CDFs as n goes to infinity, then the CDF is eventually going to converge to a standard Gaussian. Of course, making that mathematically precise is very complicated, but at least you see here what would be the actual mathematical statement that we would prove. Instead of doing that, we're going to look at some applications of the Gaussian approximation inspired by the central limit theorem to probabilistic modeling and to statistics. A common application is to approximate the distribution of a binomial distribution, of a binomial random variable. So a binomial random variable with parameters n and theta has this PMF, but if you remember our definition of the binomial distribution, which is already a while ago, what we said is you can imagine it as flipping n coins, which are independent, and each of the coins is equal to 1, or it's equal to heads, with probability theta. So we can actually write this binomial distribution, this binomial random variable, as a sum of independent Bernoulli random variables, each of which has mean theta and variance theta times 1 minus theta. So we can apply the central limit theorem here. The central limit theorem tells us that if we divide this by n to get actually an average, so we get exactly the statement that we have in our central limit theorem, then that is going to have this quantity is going to have a distribution that is approximately Gaussian with mean theta, which is the mean of each of these guys, and variance equal to the variance of each of those guys divided by n. But we're actually interested in the distribution of A in this case. So what is the distribution of A going to be like? Well, if this is Gaussian with this mean and this variance, we just have to multiply the mean by n and the variance by n squared. So we get that the binomial is Gaussian with mean n theta, which is the mean of the binomial, approximately Gaussian, which means with mean n theta, which is the mean of the binomial, and variance n times theta times 1 minus theta, which is the variance of the binomial. So now we're going to use this approximation to do some probabilistic modeling. Here we want to compare two possible strategies of a basketball team. In one of the strategies, the team only shoots 2-point shots. And in the other strategy, the team only shoots 3-point shots. And to compare these strategies, we're basically going to make them play against each other. This is kind of the game here, what we're trying to model. We're going to assume that each of the teams, strategy 2P team and strategy 3P team, shoots 100 shots that are independent Bernoulli random variables with parameter 0.5 when they shoot 2-point shots, which is a typical percentage for 2-point shots in basketball, and 0.35, which is a typical percentage for 3-point shots in basketball. Okay, so again, one of the teams shoots only 2-point shots with that percentage, and the other team shoots 3-point shots with that percentage. And now we're going to model what happens. The shots made by the strategy 2P team are represented by this random variable, and the shots made by the team that only shoots 3-pointers is represented by this other random variable, x3p. We can see quickly that the random variables are going to be binomial with parameter n100 and parameter theta equals to 0.5 when we shoot 2-pointers and 0.35 when we shoot 3-pointers. We're actually interested in the points, right? In basketball, what matters are the points, not how many shots you make. So for the points, we're going to multiply the shots made for each of the strategies times the value of those shots. 2 when we shoot 2-pointers and 3 when we shoot 3-pointers. And what we're interested in is the score difference. Okay, who is going to win? What is the difference between the score, the number of points scored by the 3-pointer strategy minus the number of points scored by the 2-pointer strategy? Okay, and now it's when we are going to use the Gaussian approximation to make our life easy. We could compute everything exactly, but it would be quite painful. I mean, with a computer maybe less, but we're going to see that the Gaussian approximation allows us to do this very quickly. Okay, so the number of 2-pointers that we make is binomial with mean 100 theta 2 and variance 100 theta 2 times 1 minus theta 2. So our approximation is that it's going to be a Gaussian with that mean and that variance. Now, if that is approximately Gaussian with that mean and that variance, if we multiply by 2, we multiply the mean by 2 and the variance by 2 squared. So if we plug in theta 2 equals to 0.5, we get mean 100 and variance 100. For the 3-pointers, the mean is 100 times theta 3, and the variance is 100 times theta 3 times 1 minus theta 3 for the same reason. And now we're multiplying times 3 this time. So the mean gets multiplied by 3 and the variance gets multiplied by 9. And when we plug in theta 3 equal to 0.35, we get these values for the mean and the variance. And now if we want the difference between the number of points scored by the 3-pointer strategy and the number of points scored by the 2-pointer strategy, we're basically subtracting two quantities that are approximately Gaussian. And here we remember that we proved that when we sum two Gaussians, we sum their means and we sum their variances. If one of the Gaussians, is multiplied by -1, then we're going to subtract one mean from the other, and we're still going to sum the variances. Okay? So the distribution of the difference is going to be 105 minus 100, that's going to be the mean. Okay, this guy minus this guy is going to be the mean. And we have to sum the variances, and we get that variance. If we plot the approximate distribution of the 3-point strategy and the 2-point strategy, it actually makes quite a lot of sense. So we see that because with the 3-pointers, on average, we're scoring more points. It seems that, we have a higher probability of getting more points here, but we also get more variance. Okay, so notice that we have more probability of actually a catastrophic defeat if we're scoring 3-pointers. And now that in the NBA a lot of teams shoot a lot of 3-pointers, you do get these games from time to time where a team doesn't make any 3-pointers, and it's completely catastrophic. If you follow basketball, you might have seen one of those games. Now, if we look at the score difference, this is the distribution that we have derived. It has mean 5 and variance like 300 or something like that. We can integrate to compute the probability that the 3-point strategy wins. And for our model, that probability is 61%. This is a Gaussian approximation. I can also do a Monte Carlo approximation to get a pretty accurate answer, because I used a lot of Monte Carlo simulations, and that gives me 60%. So you can see that this back of the envelope calculation based on the central limit theorem approximation is actually very good and very quick. Of course, we have assumed independence. If you want to do a more nuanced analysis of basketball strategy, you probably want to include some dependencies, not only 2-pointers and 3-pointers and so on. And for that, probably you're going to end up going with Monte Carlo simulations. But here you see that the Gaussian approximation provided by the central limit theorem gives us a good, quick estimate of what is going on, as long as we assume independence everywhere. And by the way, if you don't follow basketball, in the last years, teams are increasingly shooting 3-pointers. And at the end of the day, it's because of this. Like a 3-pointer is worth 3 points instead of 2. It's as simple as that. And if you manage to put your 3-point percentage up by a bit, it really pays off in terms of winning games. All right, so now let's see the implications of the central limit theorem in statistics. Imagine that we want to estimate a population mean for a population that has a certain population variance. If we have random samples selected independently and uniformly at random from the population, we have seen over and over that the sample mean of those random samples has a mean that is equal to the population mean, and a standard deviation, which we call the standard error, which scales like the population standard deviation divided by square root of n. The central limit theorem says that as n grows, the sample mean is going to converge in distribution to a Gaussian that has mean equal to the population mean and standard deviation equal to the standard error. And we're going to use this to build confidence intervals in one of the following videos. But before that, let me show you that actually this is true. Before even that, the formal statement would be, again, that if we standardize the sample mean, we're going to see that this object is going to converge to a Gaussian with mean 0 and unit variance. Here, what I'm going to show you is a histogram of this object, which is an approximation to its PDF for actual data, which is, again, this height data where we have a population of 4,000 that is going to be our ground truth population. If we take n random samples and we look at the histogram of sample means, where we take sample means over and over and over and over just to take a look at what the distribution looks like, the standardized sample mean looks Gaussian with mean 0 and standard deviation 1 as predicted by the central limit theorem. Even for n equals 20, which is very small. For n equals 100, we see the same thing, and n equals 1,000, same thing. I mean, it's only going to get better when we get more n. Realize, by the way, that this is just to sanity check that the central limit theorem holds. In practice, we would only get one batch of samples of size n, and we're going to see how to deal with that when we talk about confidence intervals. Now let's go back to the Chebyshev bound, which basically here we're trying to see whether the bound that we use within the proof of the law of large numbers gives us a good approximation of this probability related to the sample mean that is approximating the population mean. The approximation was terrible. It was a bound, but it was terrible. What about the central limit theorem? Does it give a better approximation? And it does. The approximation is spectacular, basically. All right, so what have we learned? We have learned that the sample mean of independent random variables with finite mean and variance converges in distribution to a Gaussian. And we have seen that the Gaussian approximation is often very accurate for finite data, even when we're averaging over a small number of data. And we saw some examples of the application of this phenomenon to probabilistic modeling and to statistics. And that's all I got. Thank you very much.